Let's do chapter 19, practice problems. I already started number 1 here, so let's see what I already wrote down. We have the current in an electron beam in a cathode ray tube is measured to be 70 microamps, so 70 microamps is the current I. How many electrons hit the screen in 5 seconds? So 5 seconds is T, is the time. And then E here is just the charge of a proton or an electron. So an electron is a negative charge, so the charge of one electron would actually be negative 1.6 times 10 to the negative 19 coulombs. So that's just something that you need to know. And then we have that we're looking for how many electrons hit the screen. So to do that, we need to know, well, what's the charge that's flowing. So use our equation for current, that's the flow of charge per time, Q over T, and solve for Q, and we're going to get the current multiplied by the time. So we're going to get a total charge of 350 microcoulombs. Now, this is because when we defined current, we said it was the flow of positive charges. So that's why this charge is positive. But really, since this is talking about the number of electrons that are hitting the screen, then this charge is really negative if we're talking about electrons. And then to find how many charges there are, this is an equation we learned earlier, that the charge is equal to plus or minus NE, where N is the number of charges and E is the charge on a proton. It's the positive number. And that's why if you're looking at the charges on electrons, and you would use the minus here. But in our case, we really don't need to worry about this plus and minus because this charge was defined as the flow of positive charges. We're looking at the flow of negative charges. The number of charges will be the same. We're not worried about the direction right now. So just use this equation right here to solve for N, and it's going to be Q over E. So do 350 microcoulombs. Remember that micro means 10 to the negative 6 divided by 1.6 times 10 to the negative 19 to get a positive number of 2.2 times 10 to the 15 electrons. Let's look at number 2. This one is a simple application of Ohm's law. It gives you the resistor, so that has the resistance, and it gives you a 9-volt battery, so that's the potential difference. You can always look at the units to help you define the variables, and we're looking for current. So whenever you have R, delta V, and I, then you know that you're using Ohm's law. Ohm's law is written as I equals delta V over R. So all we have to do for this one is 9 divided by 3 to get 3. Number 3, the unit of current. Well, using the same equation here, potential difference is in volts and resistance is in ohms. So that must be the units for current, even though we use amps. This is equal to amps. But volts per ohms is also accurate. Let's do number 4. Here we are looking for the resistivity of the metal that's going to affect the resistance. So we're given a 0.2 meter long metal, we're given the length L, we're given the radius. Now we will want to convert that radius to meters, so 0.01 meters. The length was 0.2. And we're given the resistance. Oh, so I have two R's here, so let's call the resistance the big R, but let's call the radius, let's just call it small r so we don't get our R's confused here. So the resistance is 3.2 times 10 to the negative 5. And we're looking for the resistivity. So you know that resistance depends on resistivity with the equation that the resistance is the resistivity times the length divided by the area. So we know the length, we know the resistance, we're trying to find the resistivity, we need to know the area. So on the side, and because this is a quick problem set, I didn't calculate all the numbers, but on the side you want to go ahead and find the area, which is pi r squared. Whenever we're talking about a wire, we're talking about a cylindrical wire, and the charges are flowing through this way, and they're flowing through this area, which is always going to be a circle. So pi r squared is the area of a circle. So you do need to multiply pi times 0.01 squared to get your area first. And then you need to go ahead and solve for resistivity, which is going to be equal to R times A over L. And then plug in the numbers. We have resistance here, the area that you found right here, divided by the length, and we should get a resistivity of 5 times 10 to the negative 8. I think we might be able to go ahead and just finish this whole problem set here. Replacing a wire resistor with another of the same material and length, but with 3 times the diameter, will have the effect of changing the resistance by what factor? So this is very similar to the your turn example that we did in class. So you're changing some of the variables. You want to find what's the relevant equation. The relevant equation is the resistance is the resistivity times the length over the area, because you're changing the characteristics of your resistor. So the thing is that this time it's telling us diameter. That's not one of the variables, but we know that the area is related to the diameter, because the diameter, I'll call D, is equal to 2 times the radius. And if we are doing 3 times the diameter, then that just means that really we're doing 3 times the radius. So it could have said, but with 3 times the radius, because diameter and radius are just different by a factor of 2. If you triple R, you're tripling D. So if you're tripling D, you're tripling R. And then we have to use the equation. So let me just say that R2, the new radius, is 3 times the original radius R1. And then the area, the initial area, A1, was pi r squared, so pi r1 squared. So let's just plug that in here to find the initial resistance. Sometimes it's easier to put in 1s and 2s. So the initial resistance was the initial length divided by pi, the initial radius, squared. And now we want to see what happens when we're doing the same material, same length, but 3 times diameter. So now, I'll do it over here. For R2, it has the same material, the same resistivity, the same L, same L1, L2 and L1 are the same, but the R2 is 3 times R1, so pi 3 times R1 squared. And what you'll notice here is that you have 3 is squared, and that's going to mean that you're going to have a factor of 9 in the denominator. You're going to have rho times L1 divided by 9 times pi R1 squared. So we have a factor of 1/9 in front of rho L1 pi R1 squared, in front of our original resistance. So you could rewrite this as 1/9 times R1. So the factor is 1/9. Number 6. We have a wire and the temperature is changing So that means that the resistance will increase because we increase the temperature, that increases the resistance. So this is a plug and chug. The resistance is given by the initial one times 1 plus alpha times the final temperature minus the initial temperature. So this one is a plug and chug, and just make sure to plug in the right numbers. This was R initial, this was T initial here, this is alpha, that coefficient of resistivity, and then this is the final temperature. So we're given R initial, alpha, T final, T initial, so just plug all of them in and you should get 26 ohms for the new resistance, which makes sense because the resistance increased because you heated it up. So you could already cross out these ones just before even starting. Let's do number 7. A lamp has a resistance of 120 ohms, operates 100 watts, wants to apply the voltage. So we did kind of a similar one in class. This one's a little bit easier here. 100 watts is the power. And then the resistance is 120 ohms. So we can use the equation that relates the power to the voltage and the resistance. V squared over R, this is one of the 3 equations. And then we have to solve for the potential difference. So V squared equals P times R. So take the square roots. The square root of P times R will give you the right answer. So the square root of 12,000. And we'll get 110 volts. So that means that this lamp is not getting the usual 120 volts that we get from the outlet, but somehow it's getting 110 volts. And the last one, when a light bulb is turned on, its resistance increases until it reaches operating temperature. What happens to the current? Well, this is a conceptual one. When the resistance increases, that means you have more resistance to the flow of charges. That means you have less current. Now, a light bulb is not an ohmic device, but if you still consider Ohm's law, this also helps to remind you that as you increase the resistance, because it's in the denominator, the current is going to decrease.